Welcome to our next video. In this session, we're going to be talking about friction and the effects that it has on objects. Now, friction, by definition, is a force of resistance that acts against a body that is trying to move or on the verge of moving. Okay, it can be a preventative measure. We're going to approach this a little bit differently than what you may have seen in your physics classes. We're going to try to do this more as a logic kind of problem, and we'll be using this logic to help us determine which behavior actually occurs first when we start talking about things like sliding or as tipping or anything like that. All right, so the basic premise of friction looks something as follows. Okay, if we looked at a normal object, in this case, say just a block that's acting on some surface. Okay, up until this point, all the lessons that we've talked about, we had neglected friction. But we look at an object that has some weight and it has a force P that's wanting to push it, then Newton's laws say that this object wants to move in reaction to that force, right? Force equals mass times acceleration. Here's my force. The weight is part of the mass. This is actually mass times gravity, as we all recall. Okay, and then the response of this force on this object then would be some sort of acceleration as a result. Okay, but what we hadn't considered was any sort of resistance that might occur at this interface. Okay, so if we look at this, before this we had neglected that, but now we're looking at kind of an idealized situation in which what happens if we have a rough surface on this and that causes some sort of friction or resistance to develop? Obviously, Newton says that if the force hits this block, the block wants to move to the right. Okay, and that defines our direction of motion. Well, friction is always fighting the intended direction of motion, and it always occurs at these interfaces of one object moving relative to the other. All right, so if we take and kind of try to take this thought and try to extend it to a Freebody diagram of the object, okay, what we see is that we get our weight W, we get our force P, okay, that is now located at some position. We have to start tracking where these things are located. Okay, and so we have a height H, we have, and then in response we said, you know, if this object had wanted to move to the right, the friction would oppose it. Well, the only place it can be is at that interface, right? It's when I cut this object away and I look at it, you know, that's what exposes this F force. Okay, and that's the guy that's acting kind of on the interface here. All right, and so this friction, because we're moving to the right, friction has to be opposing us, acting to the left. Okay, and what happens is normally when we didn't have friction on this object, we knew that we had a reaction from the ground based on the weight, right? The weight pushed down on the object and the ground pushed back. Again, another one of Newton's laws. But what happens when friction shows up is now, if I sum forces in the x direction here, we know that this force P has to be equal to this force F. Okay, but they're separated by a distance. All right, and so this P and this F form a couple that wants to cause a rotation, in this case that's going clockwise, making the object want to rotate clockwise. Well, to maintain equilibrium, what happens is the normal force that was normally here, directly underneath the W, in order to maintain the rotational equilibrium of the vertical force, okay, now has to drift over to form a couple with the W that will resist that original rotation. So if you look at W and N, they're now separated by a distance, and what we'll do is we'll call this as a distance X, and that X distance will tell us how big a moment we can generate. And so this N starts to kind of move as I increase the force or I increase friction. This X starts to increase and this N starts to drift its way over, okay, from its original, you know, static position without friction to some new location. Okay, and it's in response to generate the moment that now N and W are forming a counterclockwise moment which will resist the one that P and F were causing. So that's kind of the basis. Okay, so this X parameter becomes an issue because if I have too small an object and N has to move out beyond the boundaries of the object, I now have an unstable situation that there's no way that a force acting way out here could be hitting on this block. All right, and that would be, you know, an impossibility. And so this X becomes one of the checks for what we call tipping for our object. Okay, so the nomenclature that we're going to use on this then for most of the objects is that we're always going to call F as a friction value. That's the friction for equilibrium, if you will, and then N will be the normal reaction, because we're going to find out that there's a relationship between N and F. Okay, now the question becomes, well, where does friction come from? Okay, so we've just said that there's this resistance that occurs, but we could have two machine parts that are very, very, very smooth, but there's always some frictional value that will occur between even the smoothest of pieces. Okay, and so friction comes from a number of locations. It can come from some sort of mechanical interlocking, which is what we show here, that if this is the bottom of my object at a microscopic level, and I know it's kind of a horrible picture, but it gets the idea across, that you have high spots and low spots on this, and then the ground will have similar high spots and low spots. And as this object tries to move, it's these low spots that tend to they fall into the valleys down below, or they get hung up, and that's where there's a little bit of resistance that happens. And so the theoretical approach to friction is that, every one of these guys would generate a resistance at its point of contact. Okay, and you could have millions of these things at the microscopic level. So what we don't want to do is have to go through and calculate all of the individual F values and all of the individual normal forces that would exist at these locations. It would just be too cumbersome. So what we're going to do is we're going to kind of deal with like an average effect. So we're going to take all of these little F1s, F1 and F2 and F3 all the way out to Fn, however many of them that we have, and say that all of those guys added together produce this single F. All right, so that way we don't have to worry about this on down on the microscopic level. Instead, we're going to deal with kind of a total combined resistance, and say that in order for one of these to move, they all have to move. Okay. All right. Now there are a couple of different types of friction. Okay, if you've ever tried to move, a refrigerator at home, on linoleum, you know that it's pretty hard to get it moving. Okay, but once this is, maybe I have, some object I'm trying to push here, at first when I try to move this fridge, on your kitchen floor or whatever, it doesn't want to go anywhere. Maybe it's dug into the linoleum. It's really hard to get it started, but even if it doesn't dig in, it's still hard to get it going. But once I get it moving, all of a sudden you can keep it moving a whole lot easier. Okay, now there's still a resistance that occurs. Okay, and that's with while it's moving. That would be our kinetic friction in that case, but we're going to focus mainly on the first case, which is the static friction. It's the amount of resistance up until the point in which this object starts to move. Okay, so we're going to label this kind of as impending motion. All right, and that's going to be kind of the basics of everything that we're going to look at. Okay, so we're going to go all the way up to the point that it wants to move, but not move, because the definition of statics is objects had to be in equilibrium, which meant they couldn't be moving. So if we go right up to that line, right before it starts to move, we're technically still in a static state. Okay, and so we're going to be looking at the friction value of that part. But be aware that when you move on to your next engineering classes, dynamics or whatever it is, dynamics will be a different animal that you'll tackle differently, and you'll have to recompute that F value for a dynamic case. Okay, and that will be one of the the first lessons that you do early on in that particular class. Okay, so static friction occurs when the object starts at rest, and kinetic friction occurs when the object is moving. Okay, all right. So we talked a little bit about this mechanical interlock. You can also get cases where maybe there's some sort of chemical reaction that occurs between two types of metal or two products, or maybe there's a glue interface that occurs here, that there's a frictional value that can be caused by some sort of chemical reaction as well. And there are a lot of different factors that factor into this friction. So we're just going to consider just the normal generic F, okay, this kind of average effect that we're looking at. Okay, all right. Now, if you recall from any physics class that you may have had in the past, okay, you can recall that they always define the friction value as being this mu times n. Okay, and so this is the way that it's classically defined for static friction. Okay, now the mu, we're going to put a subscript of s to indicate that it's a static case. Okay, that it's a coefficient of static friction, and then n is that normal that we were seeing up here. So the coefficient of friction is based off of the materials that we're looking at. The rougher materials have higher mu values, and so depending on the weight or that normal force, I get a higher resistance when mu is higher for a given object. Okay, this is one of the reasons in moving machine parts. and stuff, we try to reduce this guy as low as possible. Think about your engine, the pistons in your engine block. One of the things that we have is we have some sort of oil lubricant or something in order to try to keep this down, because when friction occurs, we get that resistance, but we also generate heat, which can lead to other problems. Okay, but again, that's kind of beyond the scope of this discussion. Okay. Now, what we'll look at, we'll define another term that you may not have seen, in your prior physics class. That if we go back and we look at our forces that we had an F that was here, and then let's say that I have, draw this guy, and that's my normal happening there, that we have two forces on this. We know that we can turn this into a resultant of those two forces. Okay, and the orientation of those resultants off of this normal direction is known as phi s. Okay, and you can kind of see, going back to our components, that the tangent of this angle would be equal to then the opposite f over the adjacent normal. Okay, and so that's exactly what you're seeing in this formula, except now I've taken the tangent from this side and put it over here. Okay, and if we say that at the point that something has reached this limit of f equals mu times n, then that will allow us to calculate our resultant on this. All right, that it turns out that angle of this is related directly to that mu value. Okay, if I kind of do the math and kind of rearrange, I'm taking an f, okay, and I'm putting that over my n. Well, we know that is mu times n over n is equal to mu. That's where it's coming from. Whoops, get that down there. I wrote a little too low. Sorry about that. Okay, and so you can see f over n, and then mu times n over n is equal to our mu value. Okay, and so that's kind of where this angle of friction, and that can be another check for us as well, because what happens is if you have an object that's not moving at all, that has no horizontal force, you have no friction because the object isn't moving, and your normal is acting completely vertical here. All right, and at that time your r starts to act in a vertical direction because there's no F component. But as you start to increase the force, that P force on your object, and you start to develop this P because the object is wanting to move, what happens is that F couples with the N and starts to kind of incline the R, and eventually the R just kind of keeps moving and moving and moving and moving a little bit further, until it reaches some limit, at which point it then breaks free and is able to start to slide. Okay, and so that's one of the other logic checks that we'll start to look at. Okay, we'll be talking about sliding as a phenomenon, and then we've already kind of mentioned the tipping as a phenomenon for simple objects. Okay. All right. And so that's what we're going to look at. Now, the way that we put all this together, okay, we've talked about impending motion. Okay, the impending motion, we said, was an object's desire, or, that it was wanting to move. So if we go back to our original block, the impending motion direction, okay, is going to be equal to, that's my impending motion, right? Okay, that it's wanting to move this way. And again, we said friction fights the direction that this object is wanting to move at that location. Okay, so what we're going to do is we're going to kind of define this thing a little bit differently. We know that if I come in and instead of saying Fs, I say that this is some Fs max on this, then what happens is if I set this to the limit at which, replace that Fs with Fs max, the moment that my force P exceeds what the object is capable of resisting, then movement will occur. Okay, and if my P is less than this amount, then no movement will occur. Okay, but we could still get a tipping phenomenon. Again, I'll show you that here in a second. All right, but that's kind of the premise of what impending motion is, and this becomes the logic. It's an inequality that exists, that P greater than Fs max it moves, and P less than Fs max it doesn't. And that will be kind of where we're going with this. Okay. Now, because we're neglecting, the chemical effects and the other resistances of this, okay, a lot of times we refer to this as static or dry friction. Okay. The facts to remember, the characteristics are that friction force, our Fs, is tangent to the contact surface in the direction opposed to the relative motion. That's our impending motion statement. Okay, and that static friction is always greater than kinetic friction. Again, once we get that refrigerator moving, then it's a lot easier to maintain it in a moving orientation. Okay, all right, so let's look at what we can kind of do. We got a simple little example kind of to show you how you start to set these problems up. Okay, and so what happens is that, maybe I have, two surfaces, and this could be, like a ladder, the side of your house and the ground. Okay, and we say that this object is oriented at some angle theta, and that it has some weight initially, and that it's, initially at rest. Well, if we think about, what happens when this thing does start to move, this is the static case, right? And if I go through and I draw my object back in the days when we weren't considering friction, I would have, a little bit of a normal here, and I would have a vertical happening there. Okay, and this is actually, it's a, and oops, sorry, I got to get the W in there too, that there would be a W acting on this, right? So two reactions, this is unstable, right? And the way that you know that is I take my normals and I line them up and they cross at a point somewhere out here. Well, unless that point is directly in line with the W, there's no way the sum of moments on this object can be zero, all right? And that's what would cause this object to slide. So this ladder, if you will, has to have something that's holding it in place whenever there's a weight. This could be the weight of the ladder, it could be the weight of the person that's on their ladder painting their house, or whatever the case may be. So friction becomes a necessity on certain objects like, like ladders. Okay, so if we look at that and we try to draw, well, what's the free body diagram look like on there, we can come over and we look at something like this. So obviously, if this ladder ever starts to fall down and gravity is acting down, then this point wants to move downward. Okay, and so the impending motion of this point for this interface is down, which means the friction resistance value at that point has to be up. So I'm calling this as point B, and I'll call the other end as point A. At B, we know that we had that normal reaction at B, and then I have this vertical at FB. Okay, and that's because the impending motion of this point was acting downward. We have the self-weight on this. Okay, and then likewise, this point, if this piece wants to go down, and we assume that this ladder doesn't get shorter like an accordion or anything, that it stays the maintained length, as this comes down, that has to move over to the left. Right, so the impending motion of this guy now is to the left, which means his friction value has to be to the right. And that's what you see on this picture. And that becomes our static free body diagram involving friction for this. All right. Now, we can apply all of these concepts not just to simple pieces. We can even go so far as to include them on frames and machines on those. And so, maybe this is now, instead of being, an extension ladder on the side of your house, now it's a step ladder. Now, friction is obviously not just for ladders, but they make for good examples in what we're doing. So I have this A-frame, okay, that would be a frame and machine, and I know it's a frame and machine because the load is here in the middle, not acting on one of the joints. All right, so there's some bending that would occur here, but I can still do the free body diagram, okay? Now, for all of these, we're going to say that maybe A has a coefficient of 0.3 and C has a coefficient of 0.5. Okay, and we can start to kind of look at, well, how can I tackle this? Well, it's the same game, right? If the force on this guy wants to pull this way, then this whole apparatus wants to move to the right. Okay, which means that the friction at A, its value will be to the left. And likewise, C will also want to be moving to the right, so its frictional direction will be to the left also. And then everything else is exactly the same. And I can go in and I can start to break these things up. Maybe I have, 100 kilonewton weight on this piece, and I have a force P on this, and I can start to see, under these loads, does this object want to move? Is it stable? Is it static? And that will be one of the checks, okay? But the rest of the mechanics that you've learned prior to this all still work, right? This is a frame and machine. I blow it apart at the hinges. BX to the right, BX to the left, they're opposite. BY down, BY up, they're opposite. This works, and I can still start to solve for all of these, okay? But you can see that the one thing that friction does is it starts to throw in a lot of extra unknowns into your free body diagram. So we've got to have some tactics for how we start to handle this. And one of those will be with the resultant of this guy that I showed you earlier. Okay, and that'll be one of the methodologies. All right, so that's kind of a phenomenon for sliding. Okay, for tipping, we can talk a little bit about that. I'll get this up here, okay? Now, tipping occurs, like we said, as we look at, our particular block. So maybe this is, back to our refrigerator example, okay, that I'm pushing on this with a force P, say, at the top of the object, okay, so P at some height H, and this object has a width B, okay. If I draw the free body diagram of this guy, and we're going to say that the weight of the refrigerator is W, I get a picture that looks something like this, all right. So assuming that the fridge is uniformly distributed in mass and weight on this, then I know that the location of this weight value is acting at the center of the object, the centroid of it. All right, and so that means that since we were B wide, the location of W is B over 2 at this location. Okay, and so if I do this, we know that the forces that are on this, I get, force P wants to move the object to the left, so my frictional value for sliding is going to oppose us. It wants to be to the right. And then we know that in response to this normal force, that again, P and F form a couple that wants to rotate this thing counterclockwise. So the W and the N have to form one that fights that, or in this case goes the opposite direction, which in our case is clockwise. So what will happen is that normal will take off of the line from W and start to drift this way. Okay. Now, the way that we can tell is if we're going to push on this thing hard enough, okay, slipping occurs, whenever I'm able to put enough force P in here that it creates an F, okay, that is going to be greater than our F max. Okay, so if this is our F max here, then so long as I solve for this X value, if X is between here and here, meaning that I haven't pushed hard enough that it forces this guy all the way over here so he's off the object, then it will slide before it ever tips. Okay, this is one of the reasons when you have very tall, heavy, narrow objects, sometimes they'll take, skis or a sled under it and basically extend the width of the base because it gives you more position for that normal force to drift. Because, right now, if I get to this point without the sled, if I go any further, the end goes off the object, it becomes unstable. But if I put a longer sled on it, this F value that was here can now go all the way out to here. And I can keep doing that, and that will keep objects from wanting to tip over as well. All right, so if we go through and we solve equilibrium of this, maybe I sum moments at W, or I sum moments at, at this point here is often fairly common. Okay, this is known as the tipping point. Right there. Okay, because this object wants to rotate about that, and depending on the direction of the rotation, the tipping point can move. Okay, but as long as this end stays between the tipping point and the line of action of the weight, as long as that normal stays in that range, this object will not tip. Okay, and that will be the check that we'll be doing for our tipping calculations there. All right, that will conclude our basics introduction for friction. In our next video, we'll look at some examples and some actual applications of mechanical apparatus that include this, things like wedges and belt friction, and friction on how it applies to pulleys will all be coming up in future examples. So as always, if you would, if you've got any suggestions for improvement or things that we can do to make this a little bit better, or information that you want to see more of, just leave us some feedback down below in the comment section. As always, like and subscribe to the channel, and we'll keep the videos coming. So hope you all have a great evening. Happy engineering.